So yes, this is work that I've been doing over the last 5 or 6 years now, developing theoretical frameworks, quantitative methodologies for measuring productivity, and also trying to understand what drives productivity change from an economic perspective. And in this particular paper, I've rolled this theory, methodology, measurement stuff out over data for the Australian economy at the sectoral level. And what I'm going to do today is I'm going to run through this, explain some of the key concepts and some of the key methods, and talk a little bit about productivity change in the two sectors that, one sector that I know a little bit about, and that's agriculture, and the other, of course, is mining, because that's the sector that you're particularly interested in. So I'll zero in on those at the end. So my work in this field in the last 5 years or so has been directed mainly at measuring productivity and understanding things about productivity for purposes of policy making. Okay, so the basic idea is that you can measure productivity change fairly easily, but unless you understand what's causing changes in productivity, you've got no idea what the policy responses are to increases or decreases in productivity. It turns out that decreases in productivity can be a very good thing. The mining industry is an example of this, and I'll explain why that is. But in other instances, productivity declines can be a very bad thing. And so we need to understand what it is that's causing productivity to change before we can start thinking about what's a correct or an appropriate policy response, if any. So the main aim here is to identify the drivers of total factor productivity, TFP, total factor productivity change in the economy. And there's a couple of things. Firstly, I want to use an index number that is proper in the sense that it satisfies some very basic axioms from index number theory. This is one thing that sets this paper apart. And the other thing that I want to do is I want to minimise the number of assumptions along the way that I need to make in order to identify all of these drivers. So basically, profit is revenue minus cost. Profitability, okay, is the term that economists use to refer to the revenue to cost ratio. And in a mathematical sense, you can break that out into two components, a quantity component and a price component. And the quantity component is basically an output-input ratio, and that's what we call total factor productivity. If all the outputs and all the inputs are in there, it's total factor productivity, okay? And the other component is a ratio of output prices to input prices, and that's the terms on which goods and services are traded, the terms of trade. And if you measure these things properly, then changes in the revenue to cost ratio can be mathematically defined exactly, or decomposed exactly into this productivity in terms of trade effect. Okay, so that's an equality. Now, this paper is focused on the TFP component and what drives it. And in the work that I do, you can break productivity out into a number of different things, but the key things from an economic viewpoint that we need to be looking at are, well, there's four things essentially. You can take any proper productivity index and you can break it out into four components. And the first component concerns the technology. And when I talk about technology here, let me make it very clear that I'm talking about a technique or a system or a process for transforming inputs into outputs. Okay, so inputs are things that go in, outputs are things that come out, and a technology is a technique or a system. It's not a product, right? So this computer is not a technology; it's a product, right? There's a factory that makes those things, but there's a set of instructions or a technique or something that tells wherever this thing is made, it tells the workers how to put the plastic and the metal and stuff together to make this product. So it's important to think of a technology as I like to think of it as a set of instructions or a book of instructions, right? And in fact, there's many different technologies available there's many different technologies available to to do all sorts of things. There's many technologies available to grow wheat, many technologies available to mine coal, and firms choose an appropriate technology given the incentives that they face. But I'll refer to that set of instructions broadly, that library of books, if you like, as the technology. And improvements in technology are one thing that contributes to productivity change, productivity growth. And that little green box over there on the left-hand side is saying, well, how do you develop new techniques and so on, research and development and other stuff. That's the story there. Okay, so if you've got productivity change being driven by, or want it to be driven by changes in technology, research and development is the way to go. The second component that I focus on in this paper is the environment. Okay, so I distinguish between variables, things that firms can and things that firms cannot choose, right? So things that firms can choose, and when I talk about firms, I'm really talking about firm managers, right? The things that they can choose are inputs and outputs mainly, things that go in and things that come out, but there are many other variables that directly affect that relationship that they can't control. So if you're a small miner, one thing that you can't control is the size of the resource base. If you're a farmer, one thing that you can't control is rainfall. Right? On a case-by-case basis, these, if you like, environmental variables will differ. But it is true that the output-input ratio, right, which is what productivity is, depends on the environment. Right? In different environments, you can use the same inputs to produce different amounts of output. The maximum output that you can produce when there's no rain is different to the maximum output you can produce when there is rain, right, if you're a farmer. Okay, so that means the environment affects productivity that way. So that's the second component. And by definition, there's not much you can do about that. The environment is something that's completely outside, always completely outside the control of the unit of analysis. Okay, so nothing you can do to affect that. The next thing is technical efficiency, and what that means, that refers to basically how far you are away from best practice, right? How far you are away from the frontier, what we refer to as the frontier. And there's a couple of reasons for not being on the frontier. Very simple reasons are firms choose the wrong book of instructions from the library, right? And another reason is, if they're like me, they just don't know how to follow instructions properly. You put me in the kitchen with a recipe, right, and I'll try and make the souffle, but it won't rise, right? I just can't follow instructions properly, right? So mistakes that are made in the production process, right? They're very simple examples of where this output shortfall comes from. That's what we refer to as technical inefficiency. But another very important source of technical inefficiency occurs in non-competitive industries like mining. And in some cases, if inputs are fixed, for example, if capital is fixed and demand conditions fall, then the revenue maximising point is a point inside the frontier, right? Because in non-competitive environments, firms can choose both output quantities and price. And sometimes they can make more revenue by producing a smaller amount of output and increasing the price than they can by operating on the frontier and selling that output at a low price. And this is where lots of considerations of capacity underutilisation come in. So in the efficiency productivity framework, right, what a lot of people call capacity underutilisation is just another word for technical inefficiency. You've got some assets, okay, and you're not using them to produce the maximum output possible. In the efficiency world, that is termed technical inefficiency, operating inside the frontier. In other worlds, it's referred to as capacity underutilisation, right? Now those first three things, technology, environment, technical efficiency, they, just in terms of technical efficiency, there's two things you can do to affect that, to improve technical efficiency. If it was because people were choosing the wrong book of instructions or using them incorrectly, you fix that through education and training, right? If it's because markets are non-competitive, right, then you fix that by processes of microeconomic reform, national competition policy, right, price regulation, all that sort of stuff is to do with that component of productivity change. Now, technology, environment, technical efficiency, improvements in all of those things. Improvements in all of those things are going to lead to improvements in productivity. Okay, and they're also going to lead to improvements in profitability. And so those three things are unambiguously good in the sense that they increase both productivity and profitability. But the last one down there, scale and scope, economists talk about economies of scale and economies of scope. And that's, so economies of scale is just how big you are. And economies of scope is, are you choosing the right input mix, the right output mix? I do a lot of work in agriculture. Irrespective of prices, there's an optimal seeding rate, right? If you're planting wheat, right, there's an optimal rate at which, optimal seed to land ratio, right? There's an optimal ratio of, in mining, trucks to labour, right? You have one driver per truck, or maybe two drivers per truck, right, okay? But, having 2 trucks and 1 driver isn't going to help you, right? That's not an optimal mix, okay? So output mix, input mix, that's all to do with economies of scale and scope. And increases in scale and scope, efficiency, can lead to, they will lead to increases in productivity, but not necessarily profits. Because different inputs and outputs associated with different prices. The thing that drives changes in scale and scope are basically things that change prices, right? So macroeconomic policies that change interest rates, minimum wages, they change the relative prices of capital and labour, and so we get different capital to labour ratios in different sectors, in different countries, right? So different countries will produce the same product using very different capital to labour ratios because of differences in prices. Macroeconomic policies that affect prices, competition policy that affects prices, anything that affects incentives will change scale and scope. Anyway, so that's basically the story. Competition policy affects the scale and scope, it affects the output and input prices, it affects... This is the policy kind of framework, okay? So this is where we're heading. And what I'm going to do over the next 15 or 20 minutes is just basically take you through the maths, right? I'm going to try and make it as simple as I can, right? Take you through these concepts, try and make them a little bit more rigorous, and also then roll out a few results for the Australian economy, and we'll have a bit of a chat about how this all fits in. Okay, so for simplicity, in terms of notation, the data that I'm going to be using is data that aggregates all the outputs up into a single output. Big Q is output, and in economics we represent technologies using functional relationships, production functions, and here on the right hand side, this big K, economists can't spell, so K stands for capital, right? L for labour, M for materials, and Z is standard notation for environmental variables, things that are outside the control of the firm. And this is the basic kind of model in economics for a simple or aggregate production function. This is the function. This little superscript T here indicates that this function changes over time, right? So that's technical change, all right? And so this is the basic relationship. This inequality here reflects the fact that this function on the right-hand side is the maximum output possible, and the actual output we observe might be less than that, okay, because of inefficiency, right? That's technical inefficiency. So that's the basic model, and in economics, the standard way forward to measuring productivity is traced back to a Nobel laureate, Robert Solow, his paper in 1957, where he said, well, look, I'm going to assume that the relationship between output and inputs and environmental variables takes this form. Okay, so you've got output equal to, right, so immediately he gets rid of this, so we get rid of the technical efficiency component. Okay, so he assumes that everybody is technically efficient, operates on the frontier. And then over here on the right-hand side, omits materials. That's not such a big deal. Capital and labour are related by this function here. This is a Cobb-Douglas function. And the important thing about this is that the coefficient of capital here and the coefficient, they add up to 1. Okay, that's a constant returns to scale technology. And this bit here is a technology and environmental component. Now what Solo does is he says, I'm going to actually construct an aggregate input, if you like, equal to this function of capital and labour, and then productivity is the aggregate input, the aggregate output divided by the input, so it's an output-input ratio, is just this bit here, which is a residual. It's known as the Solo residual. And the Solo residual, some of you, in fact many of you may have even heard of the Solo residual. The Solo residual underpins all of development economics, or pretty much all of it, pretty much all of growth economics, and this is the basic model that national statistical agencies use to measure productivity. Right? What this paper does, what I'm doing today, is I'm doing something a little bit more general than that. I'm going to leave the inequality sign in there because I think technical inefficiency is an important component of productivity change, or it could be. And then on the right-hand side, I'm going to leave materials in. And so that's good. And then see these coefficients here, beta 1, beta 2, beta 3. I'm not going to constrain them in any way. I'm not going to cause them to add up to 1. Okay, so that means that I'm going to allow for variable returns to scale, right? So then I can pick up any economies of scale effects. And then I'm going to say, at the end of the day, all of this stuff could be wrong. And so what I'm going to do is I'm going to introduce a statistical noise component, okay, to mop up any errors in functional form or measurement of the variables or omitted variables or anything like that. So that's what I do. Okay, that's the relationship that I'm going to be estimating, and it's a much more general kind of relationship than this one. It accounts for inefficiency, it recognises materials, it doesn't impose constant returns to scale, and at the end of the day I'm saying, and all of this stuff could be wrong, and so I'm going to have a statistical noise component as well.
Chris, it may be helpful for this group for you to just briefly explain why the Cobb-Douglas function is particularly relevant here.
Sure. The simplest types of functions that you can use to relate sets of variables together are linear and log linear. This is a log linear function. If there was no noise, this would be a very restrictive kind of functional form, except not that restrictive. There are other functional forms that are quite commonly used, translog, quadratic functional forms, but economists will tell you, and they'll be right, that if some of the functions that we want to estimate exist, right, then they cannot, for example, be translog. If a production function exists, right, then it's easy enough to show that if a production function exists and some very weak regularity properties are satisfied, it cannot be translog. If a cost function exists, it cannot be translog. Theoretically impossible, right? And so if you want to introduce some functional form errors into your model, use a translog. If you want to keep matters simple, okay, and admit the possibility that you might be right, then you stick to a Cobb-Douglas function. What I'll do today is I'll estimate this function, and if it turns out that the estimated relationship between all of these variables leaves very little noise at the end, I'll be saying I'm happy, okay, and I'll just work with the Cobb-Douglas. If the noise component turns out to be big, I'll be saying to myself, Cobb-Douglas isn't right, okay, let me choose a different functional relationship, and that's where the econometric magic comes into play, okay? So all I've done here is take this expression and rewrite it in a slightly different way. So the first thing I did was get rid of the inequality sign by replacing it with this e to the minus u, right? So this is the anti-logarithm of minus u. And the reason I do this is that this is standard notation in the efficiency literature for an inefficiency effect, okay? And then the other thing that I'm going to do is I'm going to say, well, this is my relationship between q. It's an exact relationship between q and everything on the right-hand side. And if I want to measure productivity, I'll just divide it by some aggregate input. And this is what I get. And what I've got here is I've got a technical and environmental component. This component here is a scale and scope component. right? If there's no economies of scale, these things will add up to 1, and then there'll just be scope or mix. This is a technical inefficiency component, and this is a noise component. And that's all I'm going to do, is I'm going to estimate this relationship and see how this changes. The change in productivity is going to be due to the change in technology and environment, changes in scale and scope, changes in technical efficiency, and a little bit left over. Okay, that's it. Right? So from this point on, it's really just a matter of, yep, let's estimate this relationship, let's make some choices about what the form of this thing is, let's make a choice about what X is, how to construct it, and away we go. All right? So I could go straight to the results here, pretty much, but I have to put you through just a little bit of pain first. I have to tell you a little bit about index numbers and other bits and pieces. Just to give you an idea of what the basic theoretical underpinnings are, I'm going to tell you a little bit about technologies, productivity indexes, measures of efficiency, the stochastic frontier model, and then the application. All right? And continue to ask questions as we go. All right. So again, in terms of notation, right? So I had some big Q's and L's and M's and so on. These were aggregate output, aggregate labour, and so on and so forth. Let's just step back a little bit and let's talk generally about an input vector. X is the notation used for input vectors in economics, and Q is an output vector. Could be a whole heap of those, and Z is a vector of environmental variables characterising the environment in which firm I operates in period T. And I say period T, I could say the technologies available in period T, same thing. Okay? And this production possibility set, as the name implies, says this is the set of input-output combinations that are feasible, right, in that time period, or using that technology, in that production environment. And so it's conditioned on T and the environmental variable. Okay? And mathematically, this says the production possibility set of the firm is the set of all input-output combinations such that X can produce Q in period T in this environment. Okay? So what do economists do with this? Well, it's a bit hard to work with these things mathematically. So what they do is they say, let me make some assumptions about this. Let me make some assumptions about the technology by way of assumptions about what the technology can and cannot produce. So, for example, we say that output sets are bounded. That means that we say that for any given amount of inputs, there's a limit to how much you can produce. That's reasonable. Can't produce an infinite amount. Weak essentiality, that means that if you're going to produce something, you've got to put something in. Okay? You can't produce something with nothing. Okay? That's weak essentiality. Weak disposability of outputs, what that means is that if you produce certain output vector using some inputs, then you can use the same inputs to produce less than that. Okay, that's reasonable. Weak disposability of inputs means that if you produce certain outputs using certain inputs, you can produce the same outputs using more inputs. Okay, and these are closure properties that just basically make the maths easier. You don't really need those. The reason I maintain these assumptions is because if they exist, or if these assumptions are true, and I haven't come across anybody yet who thinks they're in any sense unreasonable, if these assumptions are true, then I don't have to work with sets anymore, I can start working with functions. If these assumptions are true, functions exist. And one of the functions that's of interest to us is this thing called an output distance function. And don't worry about the maths. This is just an economist's way of, making themselves seem important, to make things as complicated, look as complicated as they are. It's not very complicated. What this output distance function does is it basically says, look, you've got an input-output combination that might be some distance from the frontier. If you hold the inputs fixed, right, how far is it till you go up and you hit the frontier? That's an output distance function, right? It measures distance in an output direction. The input distance function says, here you are with your inputs and outputs. what happens if you hold the outputs fixed and you just reduce inputs until you hit the frontier? That's an input distance function. So these are just measuring different directions to the frontier, and the maths is, anyway. So this is defined over, yes, for any input vector, output vector, and set of environmental variables, and a particular technology, you can measure the distance to the frontier. Okay. Now, these functions are important. This is in fact a measure of technical efficiency, right? How far you are from the frontier. Okay, that's technologies. What about productivity indexes? Well, this is important. Productivity is essentially an average product, right? Okay, if I had a single input and a single output, that's what I'd have. Average product is productivity, right? The output-input ratio. When you've got multiple inputs and multiple outputs, you can't divide a vector, one vector by another. So what do? Well, the solution to this is to aggregate this output vector, this little q as a vector, aggregate it up into a scalar. And do the same thing for the inputs, aggregate it up into a scalar. And this idea of taking some aggregate output, divide it by some aggregate input, it's been around for a while, but the important thing that has been overlooked for many years is the fact that these functions have to have certain properties, right? Particularly, they need to be non-negative, non-decreasing, and linearly homogeneous. That is, homogeneous of degree 1, right? Now, if they have those properties, right, then it turns out that index numbers that we'll come to down here, index numbers have got lots of very nice properties. Properties that many economists thought were impossible to satisfy, but they can be satisfied, right? And so, if you define productivity this way, as an aggregate output divided by an aggregate input, then productivity change, right, the productivity index, TFPI, that measures the change in productivity or compares the productivity of firm I in period t with the productivity of firm k in period s, is just, productivity of firm I in t divided by, there it is. This bit here is clearly an output quantity index, and this is an input quantity index. So we've got essentially a measure of output growth divided by a measure of input growth, and the important thing is that these things are proper indexes. Okay, now a proper index is one that satisfies many axioms, and probably the most 95, 96, 7, 8, 99% of index numbers that are currently used by national statistical agencies and economists are not proper because they do not satisfy a suite of about 9 axioms that make common sense. And 2 of these axioms are important. One is an identity axiom. The identity axiom says if this vector is the same as this vector, the index number should say they're the same. Okay, that's a good idea. Okay, and another axiom is a transitivity axiom. What the transitivity axiom says is that if outputs next year double the outputs of this year, and then outputs the year after are double again, then all direct and indirect comparisons would say that outputs 2 years down the track are 4 times bigger than they are now. Or, in a cross-section context, if Salim's got twice as much as I have, and Shabir's got twice as much as Salim, then all direct and indirect comparisons should say that Shabir's got 4 times as much as me, I've got half as much as you, you've got half as much as him, that all of these comparisons should be logically consistent, right? Now you might have heard of Fisher indexes, Tornquist indexes, Malmquist indexes. None of those indexes satisfy that property. None of them, right? So what that means is that it's very difficult to make reliable comparisons of output change, input change, or productivity change. You need to stick with index numbers that have got this structure if they are to be regarded as proper indexes and if the numbers you get are to have any meaning at all, right? Okay, so there we go. Here's a couple of examples. This is an index called a low index, and it's basically an additive type structure, right? You aggregate the outputs using a representative price vectors as, if you like, measures of relative value. That's an additive function with representative prices used as weights. Okay, so that's fine. That's a proper output quantity index. Here's an example of another index. This is a geometric Young input quantity index, and it basically, this is a logarithmic type aggregation. Okay, so that's fine. And the ratio of those two indexes is a low geometric Young index. Okay, measures of efficiency. Well, I've talked about what they are. I've talked about what the drivers of productivity are. Okay, and efficiency measures are measures of, or essentially ratios of some observed quantity to some maximum possible. Right? How well are you doing? Okay? And if we were thinking about productivity, one thing we might do is compare the observed productivity of a firm with the maximum, see the star here, the maximum productivity that's possible in period T. That's a measure of how productive, that's productive efficiency. You can break that out into, well, the environmental part and the part that is due to the actions of the firm. So the environmental part, this TFP T star Z here, is the maximum TFP possible in period T in an environment characterised by Z. And this firm efficiency is basically the ratio of observed TFP to the maximum productivity that's possible in its environment. Okay, so that's the bit that the firm is responsible for. TFP compared to the maximum possible in its environment. And then the environmental component is the balance, right? The maximum TFP possible in an environment relative to the maximum TFP possible in any environment in that period. Okay. This is the output-oriented technical efficiency component that we talked about before. That's the output distance function. That's where it comes in. And the scale mix component, that's the bit that's left. It's the component of firm efficiency that remains after the technical efficiency component is stripped out. Okay? So these are all mathematically exact. So the sort of thing that you can do is, if I take, if I take this relationship here, okay, and just rearrange it, okay, and put this bloke over on the other side, right, TFP will be equal to TFP star times all the efficiency, right, and you can actually easily enough break it out. Observed TFP is a proportion of the maximum possible, and that proportion is, the product of the environment, technical efficiency and scale effects. And that's for firm I in period T. For firm K in period S, same equation, take the ratio of the two things, and productivity change is the ratio of this for firm I in period T. The same thing for firm K in period. You've got a measure of change in maximum productivity in the two periods, that's technical change. Change in the environmental, that's environmental change. Change in technical efficiency, change in scale mix efficiency. Very simple. And if this is a relationship between outputs and inputs, this is the decomposition of that low geometric Young index that you have, right? So this is exact. It's all exact, okay? And it's saying productivity change is a technical and environmental change component. This is a scale mix change component, and this is a technical inefficiency component. And there's no noise here, right? Because at this stage I haven't introduced noise. There's no noise in this function, right? But in the work that I do, I introduce noise because I'm not sure if this relationship is exact, right? I don't know what the functional form is, I don't know if there's some measurement errors or omitted variables, and so what I'll do is I'm going to introduce noise, right? And if I do that, this is what the decomposition looks like. There's a noise component at the end, right? Okay, so this is in fact, this model is the stochastic frontier model that some of you have probably come across. I went to a paper, we had a conference here a couple of weeks ago, and one of the speakers said that they did a Google search on this model, this stochastic frontier model, which is traced back to one of my colleagues, Knox Lovell, and another fellow who's currently visiting with us, Peter Schmidt, and another fellow, Dennis Eigner. Eigner, Lovell and Schmidt basically came up with this sort of structure, and if you do a Google search on this, you get 1.2 million hits in 0.29 seconds. So this is quite well known, this model. So what I'm going to do is I'm going to estimate it. Okay, so this is just an econometric model, and it's easy enough to estimate by the method of maximum likelihood. Maximum likelihood is a simple, well, you know what maximum likelihood is. Key assumptions in the standard stochastic frontier model are that these are unobserved error terms, one representing noise, one representing inefficiency, and we just make a couple of assumptions on those and away we go. All right? And that's what I've done. Okay. So in terms of application, let me just quickly run through what we've done. For the Australian economy, I've got data on 18 market sectors over 38 years. The data that I have is what's called EU CLEMS data. Capital, Labour, Energy, Materials, Services is a big world data project that's based in the European Union. And so they make this data publicly available. So I've got data on that. In that data set, there's only one aggregate output, 3 inputs, capital, labour and materials and services. These are the average cost shares. I assume a Cobb-Douglas approximating function, right? So I'm basically assuming, Cobb-Douglas type structure. And this ATZ component, right, in here, I have to actually put a bit of structure on this. And so what I'm doing is I'm including a time trend and interactions between time trends and dummy variables. And so what this is technology and environment. So what this is doing is this is accounting for variations in the production environment this time trend on its own would be variations in the production environment that change steadily over time. In agriculture, climate change. In mining, depletion of the resource base, right? These things happen fairly steadily over time. The data on this stuff that I've seen indicates that, climate change is slow, and natural resource depletion, certainly over these 40-odd years, has been fairly slow, okay, or steady. And these dummy variables here are allowing for differences in production environments across sectors, right? So environmental variables affect output in some sectors differently to others. Rainfall affects output in agriculture differently to the way it affects output in steel production, right? And so different environmental variables have different effects, and that's what these dummy variables do. They pick up cross-sectional variations in environmental variables, okay? So T represents long-term changes in environment and technology, right? So technical progress will be picked up by this as well. So this is a combined technical and environmental change component. There's a little bit of econometric work involved in establishing the properties of corrected ordinary least squares and maximum likelihood estimators. The news here is all very good. And basically I estimate the parameters of all of these variables, and these stars indicate that coefficients are statistically significant and everything's correctly signed, or at least when I say correctly signed, consistent with what we would expect. All these numbers are positive, indicating that increases in capital, labour and material lead to increases in output. Different coefficients of time trend here, it indicates improvement in technology basically. This stuff here is indicating differences in production environments in agriculture and various other bits and pieces. And for what it's worth, this model explains 98.5% of the variation log output. And so we were talking before about functional form choice, right? If this was low, I'd be scratching my head and saying, maybe I need to introduce some interaction terms or something like this, but man, 98.5%, I'm not going to bother, okay? So this is fine. And this is the story. So what I've done is I've just used these numbers, right? These coefficients, right? Here they are. They're in here, and the ATZ component, right? Where did I write it? Here they are. They're all here, right? So I can construct this stuff, okay? And now, here's productivity change, and this is all of these graphs. These are all indexes that compare productivity in different sectors. This is wood, right? The wood industry, with productivity in agriculture in 1960. So this is the reference sector and period. So this is agriculture in 1960 starts at 1, and everything is relative to it, okay? And everything is transitive, which means that, this number here is saying that productivity in the wood industry in 1992 was twice what the productivity in agriculture had been in 1960, okay? And the graph that you're interested in here, when I put this graph up a couple of weeks ago when I gave this seminar to some economists, I said, people are a little bit embarrassed about what's been happening to productivity in the mining industry, so it's hiding in behind here, right? Because of this big drop in mining industry productivity over the last 10 years, right? We'll talk about that in a moment. But for now, this is telling you that there's big differences in productivity across sectors and over time. And from a policy viewpoint, the question is, well, what's driving this stuff? Is it technology? Is it environment? Is it inefficiency? Is it scale or is it scope? Well, let's look. This is the technical environmental change component. There's a little bit of stuff here, but not much. Okay, okay, so it's probably not it. This is technical efficiency. There's nothing happening here. A couple of little blips here and there, but the story isn't here either, right? Looks like there's quite a lot of stuff happening here. Okay, scale and mix. That's economies of scale and scope, right? So it looks like there's a lot of stuff happening here. And of course, the last component is the noise. So we'll see how much is left over. Not much. Okay, so there's a little blip here in electricity, gas and water. There's in transport, something's been happening that I haven't been able to explain. But this is where the 1.5% probably lies. The rest of it, One of the things, see here on the vertical axis, everything's got the same scale, 3, 3, 3, 3. Okay, so we can go from one to the other and we can see where's all the action. All the action is basically being driven by this scale mix stuff. Okay, so what would cause firms to change their scale and mix? Well, we talked about that right at the start. Right? The stuff that causes changes in scale and scope are changes in prices, terms of trade, macroeconomic policies, and so on and so forth. Efficient firms operating on the frontier change their output mix, change their input mix in response to those things, and every one of those changes has a productivity dividend. And that's what's showing up in here. Let's have a look at particular sectors. So I've just pulled out agriculture, right? So I've actually just come here and picked out this blue line. Okay, there it is, bumping around. Rescaled it, okay, but this is the picture in agriculture. Productivity has increased by 40% over the last 40 years, being driven by steady improvement in technology and environment, right? Technical efficiency's been bouncing around a little bit, but scale mix efficiency's been changing a lot. Big changes in scale and mix, and actually if you go back through this series you can see big changes. This big change in scale mix that appeared over this period, I don't know if anybody can remember back to 1990, but this was when the wool reserve price scheme collapsed. Everybody moved out of sheep, right? Okay, so had a big change in output mix at that time. People went from sheep production into cropping, beef and so on and so forth. All of that stuff's got a productivity dividend, okay? And that's the sort of stuff that happened here. Okay, so that's you're not really interested in that, except I will say one thing. This is very aggregate data, okay? And if we drill into these sorts of things, we look at little dips in, for example, technical efficiency, right? See this little dip here? See this little dip here? There's the, why would that be? Well, you have to remember that I don't actually have any environmental variables in here. I've just got dummy variables and stuff like that. So this could be, I don't know, what would cause output to be less than the maximum possible in any given period? Drought, okay, exactly. So here we have rainfall index and the technical efficiency index. And look at this, right? As rainfall falls through drought, big drop in maximum output, big drop in observed output compared. So yes, here again, this is the 1994-5 drought, this is the early drought. This stuff can be used to explain. You can drill in and explain these things. And if I was just looking at agriculture alone, I would have included rainfall in the analysis. This is the one that you guys are interested in. This is the mining story. Big increases in technology and environments had a positive impact. Here we've got a bit of a dip in technical efficiency here, and another dip in technical efficiency there. Noise is fairly steady. It's above 1. All that's saying is that I can't quite explain the difference between agriculture and mining. But over time, it's not really there's not much in terms of the intertemporal variation in productivity that's been left unexplained. The big driver here is scale and mix efficiency change, right? So what do we imagine is happening in mining is, what are the things that change mix and scale prices? Big changes in prices, okay, have been leading to big changes in scale in particular, right? So there's a couple of things here. There's a couple of stories about mining industry productivity that you might have heard. One is this idea that capital investment in mining takes a few years for capital commitments, investments to start producing output. Right? What does that mean? Well, technically, in economic terms, what that means is that you have some capital inputs not producing anything. Right? Well, that would be measured as not producing the maximum output possible, given technical inefficiency. Okay, and so this dip here, right, is consistent with that story. Right? And also this dip here, right, from 2002, 2003, right, this is about 2003, we see this drop in technical efficiency, right, which coincides with big increase in output prices and a big investment in mining. Okay, and if this story about investment in mining, the capital investment doesn't start to pay off for a couple of, if that is true, what would you expect? You would expect to see this dip. So that's a bit consistent with that. I'm not sure whether or not that story is valid in this case, because I just don't know how capital investment is treated in this database, right? Whether or not commitments to new mining projects, whether or not that is actually measured as capital input, or whether or not it only is measured as capital input when the capital has actually been invested and stuff comes on. Don't know. But these little dips that you see in the technical efficiency component, right, they are consistent with this story about lags in production, right? But clearly the big driver here of long-term changes in productivity are scale and mix, right? We've had decreases in scale and mix efficiency for a very, very long time, but particularly pronounced in the last 10 years. For much of this period, right, those declines have been offset by technology and environment, right? So that we see productivity fairly flat through here. But this is the thing that's got the chicken littles running around saying the sky is falling, what's causing this, okay? Well, if we look at this a bit more closely, just as we did with agriculture, this is the scale mix efficiency component falling away, and what do we see with capital, labour and materials? This is a capital index, labour index, materials index. Right throughout this whole period, capital investment's been going through the roof. It hasn't, I haven't really actually, the graph gets silly. This goes off, right, and the scale gets silly. This is what's been happening to materials, right? So as capital has been increasing, materials go. So materials is mainly fuel and stuff like that, okay? So yeah, you would expect that to go up with capital. But labour has been fairly constant up until this point, okay? So what's that telling you? That's telling you that the capital to labour and the materials to labour ratio has been changing. That's the mix component, right? Changes in the input ratio. That's economies of scope on the input side, right? It's like seed to land ratios in agriculture. Here it's labour to capital ratios and labour to materials up to here, but from this point everything's going up. Labour, capital and materials are all going up in proportion. That's scale. They're being scaled up. So this is diseconomies of scale, okay? So the scale mix component, right? Most of this has been changes in input mix. Right? There's no output mix here because there's only one output in this model. But from this point here, right, things have got even worse due to, and this doesn't look like a very big dip, but just look at the scale here. This is 1, right? It's fallen by 25%. 25% in the last 10 years due to changes in essentially scale. That's the order of magnitude of change in productivity in this industry. We've had a 25% fall in productivity in this industry in the last 10 years, and this is suggesting that this is changes in scale, diseconomies of scale, right? Other industries. So that's basically it. The story in mining is a very plausible story. If you go to first year economics and you have a look at a single input, single output model with variable returns to scale, and you say, well, you identify points of maximum profit, Okay, here it'll be a point on the frontier, and then you say, okay, now what happens if output prices increase significantly? The ISO profit line changes and it takes you to a point further out on the frontier where average product has got to be lower. It's a very simple returns to scale story. And it's the most likely one in the sense that this is a model that has been estimated by the method of maximum likelihood, which means that all the parameters and all of these components are the values that are most likely to have generated the data. Okay. So that's the story. That's the story. Okay.
Wow,
Thank you
very much, Chris.